Hello everyone, and welcome to the third lecture of the Introduction to Media Engineering course. In this lecture, we are going to continue the topic of digital representation of media, which we started in the last lecture. In the last lecture, we stopped at the point where we talked about the sampling theorem and how we can optimally choose the sampling rate for a given signal that we are converting from the continuous to the digital form. Okay, so we're gonna continue this topic right now and then talk about the different forms of representation of different types of media that we talked about in the first lecture. Okay, so what we mentioned last time is that if you are converting a signal from the continuous domain to the discrete, or from being analog to digital, there are two steps that you have to do. The first step is to do sampling, as we explained before, using the sampling theorem, and we discussed how we choose the sampling rate. Second step is the quantization step. In the quantization step, you actually assign every value that you obtained, or every value for each sample, to some discrete level, one of the quantization levels that you chose to represent your signal. Now, related to this, you might get what's called quantization noise. So if we use too few quantization levels, this leads to the effect of posterization in images, or sometimes it's called quantization noise in sound. Let me give you one example here. So let's assume that we have this signal here, okay, that looks like this. Okay, and this signal is supposed to be converted into the digital or the quantized form. So as we said, the first step is to do sampling. So you're gonna pick some samples from that signal to represent that signal, right? Once you pick the samples, then after you do that, you're gonna quantize those samples. So you're going to approximate each one of these samples to the nearest quantization level. So let's assume in this example that we are going to use 4 quantization levels. This is the first one, this is the second one, third one, and the fourth one is the bottom one. So if you're doing this, then what you will do next is that, for example, if we look at this sample here, and then you would like to decide which one of the or which quantization level should be assigned to that sample, so we can draw a horizontal line here like this, and then see what is the closest quantization level to that sample. So in this particular example, the closest quantization level would be actually let me use this. It will be actually this one here, right? Okay. Now, how about the other sample? For example, if you look at this sample here, what is the closest quantization level? If you draw a horizontal line from that sample and you go horizontally, you'll find that the closest quantization level is this one. Okay. All right. So we obtain this, and the same thing. For example, if we go, let's do one more sample. If you go to the third sample, which is here, the closest quantization level would be this one. Okay. So this is if we used 4 quantization level. Now, what you have to be aware of, that once you do this, you are going to lose some of the info that were present in the analog signal. Because if we think about this sample, its actual value is supposed to be, let me point to this, its actual value is supposed to be this point. However, when you did the quantization, you are approximating it to this level here. So now the difference between the actual value of that sample and the approximated value that you got from the quantization levels, that difference represents some error, right? Some difference between the actual value of that sample and what you're actually going to store on the computer. So that is kind of error. Ideally, we don't want this error to be high. We would like to have this error as small as possible. But whenever you decide to use a certain number of quantization levels, what will happen is that you're going to lose some info, that you will have some error in that case. Okay. So anyways, in this example, we had 4 quantization levels. As I said, the bottom one, which is the 0, this is first quantization level. This is like this is again the 0 is 1, this is 2, 3, and 4. Now what will happen if in this particular example you decide to use 2 quantization levels instead of 4? So let's try this here, and let me draw that with a different color. So if we have only 2 quantization levels, imagine that you only have 2 quantization levels, then to get the range of the signal, then one quantization level would be here at the bottom here, and the top quantization level would be this one. So these are the only 2 quantization levels that you will be using. In that case, let's see one more time what will happen if we quantize based on only 2 quantization levels this sample. Now you have to check this sample. You take this horizontal line. Is it closer to this quantization level or to this one? Now it's obviously closer to the top one and not the bottom one. So what you are going to store on the hard drive, I'm going to use the black color here, what you're going to store for the sample is actually this value. Whereas the actual value of that sample is in fact the one that we have with the horizontal line. So this is the actual value of the sample, and this is what you are going to store. You see here, this is the error. All of this is an error. It's a difference between the actual value and the stored value. Whereas when we used 4 quantization levels, the error was much smaller. It was the difference between this red line and this blue line. So in general, and this will, by the way, this will happen to the other samples as well. So in general, as you decrease the number of quantization levels, here we have only 2 quantization levels as opposed to 4 that we had in the beginning. When you have 2 quantization levels, the error will be larger. Whereas when you have 4, you have less error in that case. And obviously, if you increase the number of quantization levels more than 4, you have 6, 8, 10, whatever, then the chances that your samples will match one of the quantization levels that you set will be higher, and therefore the error would be smaller in that case. Okay, so this is the idea of quantization noise, is that once you use too few quantization levels, like in this example we had only 2 quantization levels instead of 4, we get some noise, and depending on the type of media that you're representing, you get different names for that type of noise. Let's see, for example, here. Here we have an image, and that image has millions of colors. In fact, we're representing every pixel in that image with 24 bits, 8 for red, 8 for green, and 8 for blue. Now, if you have 24 bits, then this means how many possible colors can you have in your image? It would be 2 to the power of 24, which is about 16 million colors. So this image can have up to 16 million colors. Okay, now what will happen if instead of using 24 bits per pixel, what will happen if we use only 2 bits per pixel? If you have only 2 bits per pixel, the number of possible combinations that you can get out of the 2 bits is 4, which is 2 power 2. Which means that you can only have 4 colors, as in this example. So in this example, it's the same image, supposed to be the same image as this one. However, we only have 4 possible colors compared here to having 16 million colors. So this is what you see. You see, like if you look at this image, it has only 4 colors: the white, the black, the brown, and the gray. Where here we have much more number of colors. Now, when you do this, it's like, that's why they call it posterization. This looks like it's as if it's a poster of this picture that was taken through a camera. This is one thing. The other thing, of course, when you do that, you lose some details. Like if you look at the background here, we had a mountain. Now, when you look here, it looks like the mountains now has the same color as the ocean or the sea, and therefore you're losing the details. And this is why it's called posterization, or even noise in some cases. Let's look at another example here. Here, the top bar has 256 different gray levels. Okay, starting from the white to the black. Okay, and going through all of the gray levels between white and black. Now, what will happen if instead of using, so here, if you have 256 gray levels, this means that you're representing every pixel in that image with how many bits? It would be 8 bits, right? Because 2 power 8 is 256. Now, what if we try to represent that same image but only using 1 bit per pixel? If you have 1 bit per pixel, this means that you can have maximum of 2 gray levels. In that case, would be black and white. You see here, this is the representation of that image if we use just only 1 bit per pixel, all of these will be white because they are closer to the white color than the black color. This area here is closer to the white color than the black color, where here all of the pixels here are closer to the black than the white. Now what if instead of only having 1 bit, what if we have 2 bits to represent each pixel? In that case, you will have 2 power 2, which are 4 colors. You see, we have white, we have light gray, we have dark gray, and then we have black. Okay, what if you increase that to be 3 bits per pixel, meaning that you'll have 2 power 3, which is 8 colors, you get this. So anyways, if you look at these images, specifically if you look at this one or this one compared to the original one, in the original one it looked like we have smooth transition in color or gray level from white to black and the other way around. While here you see like we have those lines, they call them contours or false contours. These like separations between 2 different colors. These lines were not present in the original image. The reason that these lines are appearing, those boundaries between the gray levels, they appear because you decided to decrease the number of quantization levels, the number of colors that you have in each image. Okay, so in general, we always like to increase the number of quantization levels, like here, to have 256 different levels. However, what you are losing by doing this is that now you have representing or you represent actually this image with 8 bits per pixel. Now, one thing about this, if you look at this one actually it has 128 gray levels. So meaning that we use 7 bits per pixel instead of 8. So in this example, if you compare this image to this one, looks like there is no difference between them, right? You cannot notice the difference between the 2 images, which means that 7 bits could be sufficient to represent this image compared to the 8 bits. So although the 8 bits will give you 256 gray levels, but however for this specific image, 128 would be sufficient because we cannot, at least visually, see a difference between this one and this one. But in general, increasing the number of quantization levels will give you higher quality image. You wouldn't lose much, however, you are wasting space. Okay, so this is the idea of the quantization noise and how we should set actually the number of quantization levels in order to avoid losing details in images. Okay. Okay, now before we start talking about how to represent each type of media, we will talk in general about compression, because compression must often be applied to digital multimedia to save storage space. We always have an issue with storing data because specifically different types of multimedia, because they eat up lots of storage once you try to store them. However, we have compression techniques, and the compression techniques are really essential because without them we wouldn't have been able to maybe store most of the different types of multimedia that we have. There are 2 types of compression methods. There is what's called lossless compression and lossy compression. So what's the difference? In lossless compression, if you have some data, you compress it, you get the compressed data. If you decompress the compressed data, you get back the original data exactly the same without no difference at all. Example of this, like the zip files, for example, or the RAR. So when you have a big file and you compress it using WinZip, for example, you are compressing this data into smaller storage. But once you decompress it, you get exactly the same information that you compressed. You don't lose anything by doing it. That's why it's called lossless compression. There is another type which is called the lossy compression methods, where if you have some data and you compress it, you get the compressed data. When you decompress the compressed data, you get data that is not exactly the same as the original data. There might be slight difference between the decompressed data and the original data. Examples of this are the JPEG compression for compressing images and the MP3. So you might be wondering, what do you mean by lossy? Because when I look at an image that is stored using JPEG format, or I listen to an audio file that's stored using MP3, I don't feel that the song has changed, for example. Yes, and this is really the main idea of lossy compression methods. How you can compress data and lose part of that data, okay, during the compression process, but still the user who's going to play this media, like look at the image or listen to the music, wouldn't feel that he or she has lost anything. Okay, it's like, I know it looks like magic, but this is the whole idea of the lossy compression methods, how we can do this compression, decompression, lose some information during the process, but still we don't feel that we have lost anything. Okay, because if you feel that you have lost something, then this is not a valid compression technique. Okay, we will have one specific topic during this course, one lecture on compression techniques. We'll talk about the lossless and lossy and see different variations, but this is just an intro to what compression is, because it's really necessary when we talk about storing or representing different types of media. Okay. Okay, now what we are going to do is we're going to see each type of media, image, video, audio, and text, each one of them, how we can represent that in digital format. What are the different ways of representing these types of media? Okay, so media data may be represented as a textual description in a suitable language, or as binary data with a specific structure form. So let's see an example of this. For example, let's assume that we have this, let's look at this one first. Let's assume this is an original scene. So let's assume this is not a flower. This is not a picture of a flower. This is the actual flower, okay, the physical flower. And then we're taking a picture of that actual scene, okay? Now, once you do that, you have to decide, because normally images are displayed as arrays of pixels, like two-dimensional array, or it's like a matrix format. You have rows and columns. So you have to decide this scene that you're taking a picture of, how many rows and columns you're going to use to represent that scene. Like here, we are using 32 rows and 32 columns to represent that scene, represent the flower. Where here, we are using 16 by 16, 16 rows multiplied by 16 columns. Okay, so when you look at these two images, you can see that there is some reduction maybe in the quality of the image, and the reason is because you're using small number of rows and columns. By the way, the actual images that we see on a computer, they wouldn't be like 32 by 32. They would be much higher, like maybe thousands or hundreds of pixels. Okay, but here we have 32 by 32 image, and this is 16 by 16 image. As you can see, the 16 by 16 has a much lower quality and what we call it the resolution compared to the 32 by 32. Okay. Now, one important thing about these two images is, given that this image has 32 rows by 32 columns, each square that you see in this image has a single color. It might be more obvious here if you look at any of these, like this pixel, we call each one of those squares, we call it a pixel. Each pixel here has a single color. Okay, if you look at any, you wouldn't have multiple colors within the pixel. Why? Because this is one unit, this is one pixel, so all of the color inside is a single color. Okay. Of course, if you increase beyond 32 by 32, you might get a better quality of this image. Okay. Now, if we think about this, the 32 by 32 versus the 16 by 16, which one of the two steps that we had in the digitization process is involved here? Is it the sampling or is it the quantization? So actually, when we say we are using 32 by 32 or 16 by 16, this means we are changing the sampling. Why the sampling? Because the sampling, again, it's like you have, when we explained in the previous slide the example of the signal, we were talking that we have a signal and we are sampling from it. Same thing here, but now this is something two-dimensional. This is the original scene, and we are sampling this original scene by picking pixels out of the original scene to store. Okay, so when we say that we have 32 by 32, 16 by 16, or even 100 by 100, we're talking here about the sampling step, which of course, if we increase the number of samples, we will have a higher quality image. Okay. How about the quantization? The quantization would be when you choose how many colors you're going to use to store or to represent each pixel. Okay. So this is the idea of image representation. So the normal way of representing images is that images are displayed as arrays of pixels, and mainly two-dimensional array, something that has rows and columns. Okay. Okay, now there are actually two ways to represent an image and store it, either in the form of a bitmap or vector graphics. So what's the difference between the two? Bitmaps are what we just explained, representing an image as a two-dimensional array. So a bitmap is an array of logical pixels, stored color values that can be mapped directly to the physical pixels on the display. So for example, if you look at this image is 1, 2, 3, it's like 5 by 5 image, meaning that it has 25 pixels. The way This image will be stored in a bitmap format. You'd have a 5 by 5 two-dimensional array, as you can see here, a matrix, where every location will hold a number that represents the color of the pixel. So for example, the number that we have here is a representation of the color of that pixel. The number that we have here is a representation of the color of that pixel, and so on. Okay. Now, given that we have in this image, it's a colored image, we normally use the RGB representation, where each one of the red, green, and blue components is represented with 8 bits, which means that in total you will have 8 bits and 8 bits for each component multiplied by 3. You get 24 bits representation for each pixel. Okay. Now the first 8 bits represent the how much red we have in that pixel. The second 8 bits represent the green, and the third 8 bits represent the blue. So if you look at this image, it looks like this image is mostly blue, right? If you look at the image, most of the colors are blue, but then there are variations of blue, indicating that this blue might be mixed with red and green with some other degrees. So if you take, for example, the first pixel, which is this one, this is the color 9BB5FF. Actually, this is represented with the hexadecimal representation, where each digit is represented in 4 bits, right? So the first 2 digits, which are the first 8 bits, represent the red component. The second 8 represent the green component, and the last 2 digits represent the blue. Now, if you look at the 2 last digits that represent the blue component, they have a value of FF. You know, F in hexadecimal maps in binary to 15, and decimal 15, which is 4 ones. Okay, so it looks like the last 8 bits are all ones. Okay, so if you have 8 bits to represent the blue component, the highest value that you can have, of course, for the blue component is to have all ones, which are 255. So this means that this pixel here, the degree of blue is full blue, which is 8 bits all ones. Okay, which makes sense. Actually, if you look at most of the pixels here, the last 8 bits, they have FF, which makes sense because most of the pixels here are bluish, kind of, and therefore it makes sense to have the blue component the strongest. Now, when you look at the first 8 bits, which represent the red component, it's equal to 9B. It's still a high value, but it's not actually as high as FF, which is all ones. And the green component is B5, and so on for the other pixels. Okay, so this is what the bitmap representation is, that you're representing an image as an array of logical pixels, and each pixel maps to the physical pixel, the pixel that appears on the screen. Okay, so this is the bitmap representation. The second type that we can use to represent images is what's called vector graphics. In vector graphics, the image is stored as a mathematical description of a collection of individual lines, curves, and shapes making up the image, which requires computation to render it. And by rendering, we mean that we are generating the pixels from the model. So let's take as an example, let's assume we have this image that has a red square and an outer frame that looks blue. Okay. In vector graphics, we represent the shape using a mathematical description. So the idea here, if you would like to represent a square, for example, okay, then and you would like to represent that square not by representing every single pixel in the square as we did in the bitmap representation. No, like using a description of how the square looks like. So what kind of information do you need to store to represent that square, to say that I have a square with a certain size in a certain location in the image? Okay, so this is the idea of the vector graphics. Therefore, this is how it's done. Let's assume, let me draw it here. Let's say this is the square that we want to represent, and store some information that would tell us what is the location of that square, what is the size of that square, and what's the color of the inside of the square. Now, to represent the location of a square, one possible way is to represent the center of the square, which is the point at which the diagonals, this is one diagonal, this is the other one, the point at which the diagonals intersect, this point is, let's call it the center of that square. So if we store, let me write down here what we're going to store. So let's store the center, which is represented with an x and y values. Okay, so this is one piece of information that we need to store in order to know where the square is located. The other thing is that you might need is the length of the side of the square. Since it's a square, all four sides are equal. So for example, this is L. So you need to store L, which is the length of the side of the square. Okay, so using the coordinates of the center of the square and the length of the side, this is sufficient actually to draw the square and know where it's located in the image. Okay, the last thing is how the color of the filling. We can have additionally the color, which is what is the color that we will use to fill that square. Okay, so if you think about this, how many values you need to store? We need to store x, y, l, and color. Only 4 values, right? Whereas if this square, if you map it to a two-dimensional array, and let me draw this here. So let's assume this is how the image or how the square looks like as a two-dimensional array. Okay, then in that case, if you think about it, how many rows do we have? We have 1, 2, 3, 4, 5, 6 rows and 6 columns, meaning that we have 36 pixels. So therefore, if you're going to store that square, you have to store the color of each of the 36 pixels that you have inside the square. Okay, so therefore this, if you think about the idea of the vector graphics, the main principle of vector graphics is that once we store the shapes using some mathematical description, like in a square we're representing it with the length of the side and the coordinates and the color, you might actually be able to save storage. Okay, so one way to do this is to use something called the scalable vector graphics, or SVG. This is like a language that has been proposed in order to represent vector graphics images. So this is the code or the content of the SVG file that would describe this image. Okay, so forget about the first 3 lines. These are just like headers, so they don't have information. Actually, the line that represents this image is what's described here. It says path fill equals this. So this is actually an indication of filling the inner square with red color. And then stroke of blue outline. What is a stroke? The stroke is this part here. So this is where that represents the outer outline. And then what's the stroke width? Which is what's the size of that stroke? It's equal to 20. Okay, so this line, regardless of the details of this, I just want you to get the general idea. This line actually is a description of this image. So we were able to describe this image only using this simple line. Okay, so the main advantage of using vector graphics, as I said, is that you will be able to store an image in much less size compared to using a two-dimensional array. Okay, so in fact, this, if you count how many, let's assume that each character here is represented with 1 byte. If you count how many bytes we have in this text, it's like 284 bytes. Now, what if we are going to represent this exact same image but using bitmap? And let's make an assumption is that in the image, that the image is of a square of width 45 millimeters. So this is 45 millimeters. Okay, and let's assume we're using 24 bits for each color, because this is a colored image. So we have RGB, 8 for, as we said, 8 for red, 8 for green, 8 for blue. So we have 24 bits to represent each pixel. Okay, and let's assume that the resolution of the whatever the image here is 72 pixels per inch. The inch is 2.54 centimeters, which means for each 2.54 centimeters of the image, you will have 72 pixels. Okay, so if you multiply the numbers, like for example, we have 45 millimeter, the width of the square, so it's like 45 millimeter by 45 millimeter. Anyways, we have 72 pixels per inch. So if you count how many pixels we have per inch for the 45 millimeters, and multiply this by the 3 bytes that we have for each pixel, you will get a total of 48 kilobytes. So this image would be stored in 48 kilobytes using the two-dimensional array, which is, as I said, it's as if you're dividing this into columns, okay, as I did here, and rows, right? So you divide it into rows and columns and store the value of each pixel. If you do that, you will get a total of 48 kilobytes as opposed to only 284 bytes in the case of vector graphics, okay? So therefore, vector graphics could be useful in representing this type of image in much less storage. Therefore, we can say that vector graphics are often smaller than bitmaps. They are resolution independent and can be scaled without loss of quality. We'll see that in the next slide. But they are only suitable for certain sorts of synthetic images, not photographs. So why are we saying this? The whole idea of vector graphics is that you can represent shapes that have uniform or similar color for all pixels. For example, if let's imagine that you have a vector graphics representation of this flower here. This is the actual image saved in two-dimensional array, okay? But now, if you're going to represent that with vector graphics, then obviously you wouldn't be able, if you go ahead and try to describe each single detail that we have in that image with a vector graphics code or representation, what you will end up having, most probably, a bigger file size than the two-dimensional array. So, but if you try to get an approximation of this digital photograph, this is the approximation. So this part would be representing, like, this is how we represent the flower, and this is like the root of the flower is represented here. And this is the inner part represented this way. So if you think about it, this doesn't look like a very good representation of that image. However, it has much less storage. But anyways, if you would like to represent a photograph, something natural that you're taking a picture of, using vector graphics wouldn't be the best option here, because otherwise you will have to represent every single detail at the level of the pixel. Like imagine that you're writing a vector graphics code or SVG, like the SVG file that we had, for every single pixel that you have in the image. Then the storage will be huge actually, and you're losing the main advantage of vector graphics in that case. So for photographs, it's not possible, or it's not feasible, or it's not good actually to use vector graphics. However, vector graphics are useful for synthetic images, things that are created artificially on the computer. For example, you know, like if you go to PowerPoint or Paint or anything, or Photoshop, and you draw something, like you draw a triangle, a square, a certain shape, this is actually in the background is implemented using vector graphics. Why? Because these are synthetic shapes, things that are artificial, that are created actually on the computer, and therefore they can be represented with vector graphics. Okay, so this is the advantage and disadvantage actually of vector graphics when it comes to representing photographs. Okay. Another advantage of vector graphics is that when you scale up an image, the curves remain smooth, whereas in bitmap format they become blurred. Let's look at this. If this is you remember the picture we had in the previous slide. This is the center of the flower, the inner part of the flower in the vector graphics image, and this is the one that we had in the original image, not the vector graphics, the bitmap one. Okay. Now, if we scale them up, we just zoom in on this part and zoom in on this part. The good thing about vector graphics is when you do zooming in, it's not done by, let me talk first about how we zoom in original images. The way we zoom in original images is that one of the simplest ways is to take, for example, one pixel, okay, and copy the value of that pixel to neighboring pixels. So if you take every pixel and copy it to the neighboring two, then in that, or the neighboring at least one. So for example, you copy one pixel, you take one pixel and copy it and put it in the next position, and then take the next original pixel, copy it in the next position, and so on. Once you do that, you get a bigger size image that looks very similar to the original one. In vector graphics, the way this scaling up is done through also geometrical representation and not by copying and pasting pixels. And therefore, this actually helps in making the image smoother You see, like if you look at the edges here, look very smooth edges, while here looks very blurry and blurred. And this is a result, the blur here is a result of having this copy and paste thing to scale up two-dimensional images. Okay, so this is one other advantage of vector graphics. Okay, so therefore what we covered here, we talked about two ways of representing images. We talked about using bitmap two-dimensional arrays to represent images, and also we talked about the vector graphics, which can save storage, but it's more suitable for synthetic images and not for actual pictures that you take or scenes that you take a picture of. Okay, now we move to the next type of media, which is video and animation, and how we can represent it. So displaying moving pictures in general depends on the phenomenon known as the persistence of vision. What's the persistence of vision? It's a lag in the eye's response to visual stimuli, resulting in after images being seen briefly when the stimulus is no longer present. So the thing here, that what this persistence of vision tries to, or this phenomena, what it represents is that, let's assume that someone shows you one image and then removes that image very quickly. What happens is that image would remain in your visual system. You still see it for a very brief amount of time. And this is what we call the after image. Okay? So based on this persistence of vision phenomena, the idea of creating moving pictures like videos and animation, the idea came from this. So let me show you one example. So let's assume this is the time axis, and this is let's assume this is time 0, and this is, for example, another like time 1 right after it. So if we have one image, we call it F1, frame 1, and we display it at time 0, and then we remove it, and then at time T1 we put another frame which is F2. Okay, the thing is, because of the persistence of vision that we just described, if frame 1 is removed, the time in between 0 and T1, if it's very short time, you will still see frame number 1, and then once frame number 2 appears, you will start to see it. So the whole idea here is that given this persistence of vision idea, then we can get the feeling of a continuous motion picture. We have one frame and then another frame played after some time, but you don't feel that there is one frame that was there and then it was removed, and you don't feel that this is happening and then another frame appears. You actually feel, when you watch a video file, you feel like it's continuous, although in reality it's not continuous. There are multiple frames with time gaps between them. Okay, so the whole idea, it's like this is this lag that we are talking about might seem to be as if it's like some problem or an error that we have in our visual system as humans. However, we made use of that small error, that small lag, to our benefit, so that we can create those video and animation files. Okay, so therefore what we say here, let me erase this, that if still images are presented to the eye at a rate above what's called the fusion frequency, and usually it's like 16 to 40 pictures per second, meaning that if you display for example 40 pictures per second to someone, so every second you have 40 pictures that are displayed very quickly one after the other, you wouldn't actually feel that these are multiple single pictures to you, or it will feel as if this is a continuous video. Okay, the minimum of this is 16. So if you go below 16 pictures per second, let's say 10 pictures per second, you might start noticing that these are 10 different pictures with time gaps between them. Okay, so if you split the second into 10, like for example 1 second, you can split it into 10 portions where each portion is 100 milliseconds. Okay, if you display one image and then wait 100 milliseconds, display the second image, and so on, you will notice that these are different images played back very quickly. But above that, once you go to 16 up to 40, sometimes at 40, then you wouldn't actually notice it. Above 40 pictures per second, of course, you wouldn't notice that these are different pictures. Okay, That's why most of the display devices like computer screens, TVs, and so on, they use a number higher than 40. Actually, they use 50 or 60 frames per second being displayed. And that will guarantee that the user or the person who's watching that device will never notice that these are different pictures being played back very quickly. Okay, so to explain this idea, let's look at this video here. So what we will describe here is the idea of thaumatrops. It's a very simple toy, but it actually kind of describes this idea in a very simple way. Okay, so if you look at this here, what this thaumatrops have, they have like this circle with two different pictures on the back. Now, when you flip them very quickly, you see, you might start seeing that this is not, it's like as if you see the two objects together in one image. Okay, let's watch this one, for example. For a very small fraction of time, it might appear as if the bird is inside the cage. And here, for a very small fraction of time, it might appear as if the sun is with the mountain in the same picture, right? So this is, even if you look at this one. So why is this happening? Because when you rotate this very quickly to the user, these two images, they kind of merge together because they're played very quickly, like you see this one. So it might appear to you as if they are forming a single image, not two images. Okay, so this is the whole idea of thaumatrops and the idea of the persistence of vision and the fusion frequency is that once you do this play, like when you rotate these images very quickly, it's as if you are trying to display multiple pictures per second. And once you go to this area between 16 to 40 pictures per second, it will appear to you as if the images are merging together. That's why they call it fusion frequency, as if they are fusing together. So based on this phenomenon that we have in our visual system, the idea of video and animation was created, and using this phenomena, we can give the feeling of moving picture in that case. Okay. Now, a sequence of frames would have actually two types. We have what's called the live action, which is sequences recorded from real life, which we normally call video, and animation, which is artificially created drawn sequences. So if you're using a video camera to shoot the outside or like normal or natural scenes, this is what's called the live action or video. However, if you're creating pictures on the computer, you're drawing them and then playing back those drawn pictures very quickly, this is what we call animation. Okay. Now, video frames are stored digitally and normally as bitmapped images, which of course would require extensive compression. So let's see, as an example, let's assume we have a frame, an image. Let me draw it here. Like this is one frame of a video, and that frame has 720 pixels on the width, and it has 576 pixels on the height. So we have 576 rows and 720 columns. Okay, and let's assume in this video we are going to display that video at a rate of 25 frames per second. So every second you're displaying to the user 25 frames. If we try to estimate what would be the size of this video, assuming that this video is 10 minutes long, then this is how it would be. You have 10 minutes of video. Each minute, how many seconds do we have in the minute? The reason that we're converting to seconds is that the rate is given as 25 frames per second. So we have to convert the 10 minutes into seconds, so we multiply by 60. Now, how many frames do we have per second? We have, as mentioned here, 25 frames per second. Now, what is the size of a single frame? By size, I mean here, how many pixels does each frame have? It has actually 720 multiplied by 576. This is the total number of pixels that you are storing for the 10 minutes. Now, what is the size of each pixel? How many bits do you need to represent each pixel? Here we assume that we require 24 bits for color. So if we multiply this by 24. Okay, so if I compute this, let me calculate this here. Let's get the calculator. We have 10 multiplied by 60 multiplied by 25 by 720 by 576 by 24. So we get this number. I'll write it here: 1492992, and then 5 zeros. Okay, bits. This is the total number of bits. Now, if you would like to convert that into bytes, you have to divide that by 8. So now it's in bytes. Okay. Now, if you would like to convert that into kilobytes, you divide by 1024. So this number is equal to 18225 and then 3 zeros kilobytes. If you'd like to convert that into megabytes, you're gonna divide one more time by 1024. If you'd like to convert it into gigabytes, you divide by one more time by 1024, and then in that case, you will get a number that is somehow close to 15 or maybe 17 gigabytes. Okay, so in general, so this means that if you have 10 minutes of video and you are storing each frame or every pixel in each frame in 24 bits, and you have 25 frames per second to display, in total that 10-minute video will take about 15 gigabytes. So you might be wondering, why this big size? I can sometimes download a movie that's like 1 hour and a half, and that movie, all of it, wouldn't fit maybe in 1 gigabyte. So why 15 gigabytes for only 10 minutes? The reason here is that we're not using any compression. That's why we're saying that compression is really essential when we talk about video and animation. Without compression, we wouldn't have been able to store all these videos. The other thing is, the videos that we watch over the internet, if they were like 15 gigabyte for a 10-minute, normally if you go to YouTube, you might have a 10-minute video, but you watch it very quickly and doesn't take that much time to download or even to load. Why? Because we have compression. So because of the large size of video data, compression is always applied, such as the MPEG-4 standard, which we will talk about it later on in detail. Okay. So when it comes to animation, animations may be captured from external source or created in a computer. Animation can be created using vector graphics, which would be like a cartoon style thing, which results in small files compared to video. So for example, if you look at this, this is like an animation or frames from an animation that shows a person who's actually jumping. Okay, so this is, as you can see, this is not a picture that was taken using a camera. It's something that is drawn artificially on a computer, right? So this is actually can be created using vector graphics. Okay, and therefore animation files might be much smaller in size than live video. Why? Because if vector graphics is used to create them, then they will be actually very small in size compared to live video. Okay, so this is all about the video and animation. We next discuss audio representation. So we talked about images, we talked about video. As I mentioned in the first lecture, in this course we'll be interested in image, video, audio, and text. So now we move to the third type of media, which is audio, and how it's represented. So sound in general is caused by rapid variations of air pressure over time. This is actually how we hear sound, is that the air pressure around the ear actually changes, and that's what we hear as sound. Sound can be represented as a sequence of samples after digitization when stored. For example, CD audio is sampled at a frequency of 44.1 kilohertz. So if you think about it, why would in CD audio they use a sampling rate of 44.1 kilohertz? Why specifically this number? So one thing about audio and our ability to hear things as humans is that the highest frequency that we can hear is somewhere around the 20 kilohertz. So if around you there is a sound that has a frequency of 20 kilohertz, you might be able to hear it. Now, if you go to 30, 40 higher numbers, you as a human, you wouldn't be able to hear that sound. Although there is some sound that's present, there is some variation in air pressure that has this frequency, but you wouldn't be able to hear it because the maximum you can hear is up to around the 20 kilohertz. Now remember, when we talked about the sampling theorem, we said that sampling theorem states that if you would like to represent some signal or something in digital form and you are trying to choose your sampling rate, your sampling rate should be at least or more than twice the highest frequency you would have in the signal that you're trying to store. So given that our ability to hear, its maximum is 20 kilohertz, so this is like the highest frequency that we can hear, then if we are choosing how many samples we should use in order to store an audio file, then according to the sampling theorem, it should be at least twice that number. So if we say it's around 20 kilohertz, then the sampling rate should be around twice that number, which is around the 40 kilohertz. That's why in the CD audio, they use 44.1 kilohertz. They are above, actually, it has to be above the highest or the twice the highest frequency you can hear. So that's the reason that CD audio uses the 44.1 kilohertz. And then audio, when it's delivered over the internet, it's normally compressed, and it's often used uses the MP3 codec. As I mentioned, in an MP3, as I mentioned, is one way of lossy compression. You lose some information when you store something in MP3. The main advantage of representing audio in digital form is the digital representation of audio facilitates editing, such as slowing down the music by adding samples. So for example, if you have some audio file, you would like to make it slower, you can do that by just inserting samples in between the actual samples that exist, and that will make the sound actually slower. Okay, so this is all about audio representation, and again, by the end of this course, we will have one full lecture on audio. I will talk in more detail about this and different effects and things that we can do in audio, to audio actually in digital format. The last representation we are discussing is text representation. So we covered images, video, animation, and audio. So how do we represent text in in digital form? A character set is a mapping from characters to character codes. For example, you're probably familiar with the ASCII code and the Unicode. The Unicode is a character set capable of representing text in all known languages. So any character would have a code in any language that is represented in what's called the Unicode. Now, in addition to the value of the character itself, we have also to sometimes, or it depends on the editor, but we might be storing the font, which is a set of character shapes called glyphs, which define how a character is displayed. So other than the character itself, what it represents, is it A or B or C, we have the glyphs which represent the font, how you're going to display that character. Okay. Also, many aspects of layout must be controlled when text is displayed. So it's not only about what text that you would like to store and how it would look, also the layout of the text. For example, if you look at these two pieces of text, they have the same text, which is actually just rubbish. However, the difference between them is the font that is used and the layout. Like here, you see the paragraph is aligned with the right side, this one is not aligned. So images, although images can only be displayed in one way, words can be arranged in many different ways. You can represent the same text in this form or in this form. So this is one difference between, however, images, an image can only be displayed the same way every time. Okay, so this is all about digital representation. So we talked this way about how we can represent different types of media in digital form. We talked in this topic from the beginning that we started actually the previous lecture. We talked about the digitization process, the sampling, the quantization, how to choose the sampling rate, what happens if we use less number of quantization levels, the quantization noise that we described today. And then also we next talked about the how to represent different types of media, how to represent images using bitmap or vector graphics, how to represent video and animation and the idea of the persistence of vision, how we represent audio and the sampling rate of CD, and text representation at the end. Okay, all right, that's it for today, and I'll talk to you soon, inshallah. Goodbye.